Thank you, and welcome to everybody who joined this webinar, wherever you are tuned into today's session. I'm Harold Bornfleth, and today I will be talking about BESA Statistics 2.0 and the implementation of our ANOVA, ANCOVA, and correlation workflows, which were added in the release of BESA Statistics that came out last year. I will also give you some background about the implementation of the methods in BESA Statistics. So now what's today on the menu? We have an introductory talk about the topics: why do we need non-parametric cluster statistics? Then a little talk about one-factor ANOVA with or without covariate of no interest, and some introduction to the correlation workflow in BESA Statistics. Yeah, all this will be part of an introductory talk. And then in the second part of the webinar, we will see a hands-on demonstration using some real experimental data. And finally, I will be happy to answer questions. So, so please, throughout the presentation, feel free to send in your questions, and my colleague Avinash Pant, who's with me here at BESA headquarters, will pick up all your contributions to the discussion, and I will then try to answer them at the end of the session. So first of all, let us take a look at the issue that we face in EEG. In EEG and also MEG research, we are particularly faced with a multiple comparisons problem, as we need to compute many tests to compare two waveforms. So at a high sampling rate, there are a lot of data points in a waveform. So we would then go and perform t-tests, for example, on sample number 1, etc., on different samples. And we usually assume that a tiered t-test does not contain false positives, but of course there's always a probability that false positives will pop up. So the probability is in this case 5% for each test that we perform, assuming that the null hypothesis is right. So the overall probability for a false positive will increase with the number of tests. As shown in this illustration, some of the test results will land in the tail end of the distribution just by statistical fluctuation, even if there is no actual statistical effect in my data set. And it will tell us, though, that we do have a significant effect. And to make things worse, if we want to compare a particular time window between two groups or two conditions, we often not only want to investigate effects in a single electrode, but in many electrodes or MEG sensors. So thus we end up with a very large number of tests. And usually the typically accepted probability for a false positive is 5%. This means that if the null hypothesis is true, I would live with 5% of the tests still showing significance. So if we look at a typical ERP experiment, we can here see graphically by the purple and blue parts that we do see some significance inside a baseline interval, even where the null hypothesis should definitely be true. And the longer we observe, okay, this is another example here, the longer we observe, the more likely that is to happen. So this is an enlarged baseline here. And we're going to look into this in a little bit more detail. So now, just for the sake of argument, let's say the null hypothesis is correct. We don't have any real effect, but you can see that these tests that we now call K, L, M, and N, so some of them show up inside the distribution, but some end up in the tail end of the distribution, especially the ones named K, L, M, and N here. So these would all be false positives in my final statistics. Yeah, this is of course quite an old problem, and a possible solution was suggested by Bonferroni. A very simple solution: we just divide the p-value, so the 0.05, by the number of tests that are computed. This means that for an example experiment with a 1-second epoch, a sampling rate of 250 Hz and 64 electrodes, I will have altogether 16,000 data points, and the p-value that is allowed will thus reduce to 0.000003. So only tests with a p-value smaller than that number are considered as significant results. I think it's clear that it's highly unlikely that any effect will survive the Bonferroni correction in EEG or MEG research. And this does not mean that there are no effects present, but that the method is too conservative for EEG and MEG research, and the Bonferroni correction does not take some things into account that are characteristic for EEG and MEG. And this is that Bonferroni treats all samples as independent, which is actually not the case in EEG and MEG. We have temporal and we have spatial dependence. So effects are stable over time and also across sensors. So in other words, the same effect shows up in several time points in several channels, which means that the statistical tests in all these samples and channels are not independent tests. Thus, instead of considering individual time points, we can cluster those sampling points that show the same effect. We need to cluster the sampling points in time and in space. We're no longer going to look at a multitude of single data points, but at a limited number of clusters that show the same effect. And here we have an example of how to build a cluster. So if I just look at the time domain for the moment, I am going to check on some tests. So say we have here tests that do not surpass the threshold of significance, which we've set at 0.05 for the p-value. And at some point we get to a point where the p-value is smaller than 0.05. And this is when we start building a cluster. We now add the t-values together that we measure for these tests as long as we stay above this threshold. When we leave the threshold, again, we stop building the cluster. And in this case, the final cluster value is 20.1 for this example here. Yeah, and please note that the algorithm does not only build the clusters in time, but also over frequency and spatial neighborhood. Yeah, and spatial neighborhood, it needs to be defined. So first of all, let's have a look at the case where we have sensor data. So we're measuring on the outside of the skull, on the skin surface. In this case, BESA Statistics needs some user input. Which electrodes should be considered as neighbors? So we want to have a minimum distance value between two electrodes and sensors so that we can define a neighborhood relationship here. These values can differ between electrode caps and MEG systems, so you will put in a little bit of knowledge about your system here. If you look at images, so source images, these are source analysis results derived by distributed methods like LORETA or beamforming. Here the neighborhood structure is clear as the voxel size is the same across subjects and the position of the voxels is also known. In the case of source waveforms, here on the right, no spatial neighborhood is considered since dipoles and regional sources are considered discrete. This means that a correct source model will model the activity of only the brain region that it represents and no other activity. BESA Statistics supports data in the time domain and also in the time frequency domain. For the time domain, one extra dimension is added in the cluster neighborhood relationship, which is time. So for an image data set, for example, there will be 4 dimensions in which a cluster may grow: the 3D spatial neighborhood and the time dimension. For the time frequency domain, 2 extra dimensions are added, time and frequency. In a 2-dimensional spatial neighborhood, for example, ERP or ERF data, there will again be 4 dimensions possible for the cluster connectivity. Good, so we can now get around the multiple comparisons problem using clusters. But in order to assess the alpha error, we need a statistical distribution for the null hypothesis. We can no longer simply assume that we have a student t-test distribution where we look up the p-value. Instead, we introduce permutation testing to deal with this. So we create random data and perform the cluster analysis on these data too. And this is shown here. So imagine that we have an original distribution with two groups of subjects, like here on the left. We can now reshuffle the groups and perform our analysis. We identify the clusters with the largest and the smallest cluster value for each of the permutations, and then we repeat this reshuffle to build a distribution for the non-parametric test. So this is the first permutation here on the right, and you can imagine, so permuting many times with different groups, and each time calculating these clusters and figuring out the cluster values. So in summary, for the permutation statistics, first we identify clusters in time and space that show the same effect, and the input can be any statistical test, t-test or f-test or other tests. In the following, we then only look at the clusters and no longer at the individual time point. We then reshuffle the data, so data of subjects or conditions, depending on whether we have unpaired or paired tests, get systematically interchanged. And in these reshuffled data, we identify the clusters with the largest and the smallest values for each permutation. And these steps are repeated at least 1,000 times in order to achieve a reliable significance level of p equals 0.05. So this is an example distribution that we may obtain using these permutation statistics, and we now want to determine a probability from our cluster using this new permutation statistics. So imagine that 5% of the cluster values that we found in the permutation testing are outside of the 300 or minus 300 value for the cluster. And now I need to simply look up the cluster value in our original test and compare it with this result and check where it ends up in this new distribution. So if my cluster value is outside this 300 or minus 300 value, then I can consider it as a significant value. Yeah, so again, a summary. We have the clusters. We want them to be significant, of course. If they're significant, they need to have an absolute cluster value larger than 95% for the one-sided test, or 97.5% of all cluster values for the two-sided test derived by the permutation. These statistics are parameter-free, since the significance is estimated from a new distribution that we generate from the data sets, and the statistics can be considered corrected for multiple comparisons. Right, and now to the new introductions in BESA Statistics 2.0. So we not only offer the t-test here, but also a one-way analysis of variance. This investigates the influence of an independent variable with two or more factor levels on a dependent variable. The null hypothesis gets rejected as soon as there are at least two groups or two conditions with significantly different means. For example, EEG was measured in 10 control subjects, in 15 patients with depression, and 12 patients with schizophrenia, while they were presented words with effective content. This is the independent variable. The research question is which brain regions, EEG, MEG sensor measurements, and/or time frequency regions differentiate between controls, depressed and schizophrenic patients in emotion processing. The one that I choose to investigate is the dependent variable here. ANCOVA, so ANCOVA is about if there is another factor that influences the dependent variable, but we may not be interested in this factor. For example, we measured blood cortisol level for each person in the three groups in the above experiment, and it may have an influence on the brain response. But we don't want to investigate the effect of the blood cortisol level. We want to investigate the effect of the patient type. So we can add the blood cortisol level as covariate of no interest here. Yeah, and the ANOVAs and ANCOVAs can be computed either between groups. So this is the example that we just talked about, or within a group. For example, the same subjects listen to tones with different pitches or different intensities. Okay, so in the ANOVA, we then, after the cluster permutation, end up with a main effect. So the example here shows us a cluster shown by red voxels in an image where we have found a highly significant result. And now we want to actually know which groups differ here. So from the main effect, we still do not know was that now a difference between two of our conditions or between more than two? And if it was just between two, which of the two were the ones that had this significant difference? And to answer this question, we need a post hoc test in case of the ANOVA or ANCOVA. For the post hoc test, we decided on the Sheffey test because it's relatively conservative. So the pairwise post hoc test clusters will definitely be restricted to being inside the boundaries of the main effect cluster. And yeah, a disadvantage of the post hoc testing is that I do this in couples of conditions. So again, I'm running into the multiple comparison problem. So we need another correction for multiple comparison. And we decided on the Bonferroni-Holm correction for this. And yeah, I could now elaborate on that one as well, but that would take us too long now. So I'm going to skip that, and it's described in detail in the manual of BESA Statistics, or if you come to the BESA workshop, we can talk about it in more detail. So lastly, the correlation analysis. This investigates the relationship between two variables. It's dependent on the covariance of these two variables, so how much do they change together? For example, we want to correlate an MEG component, so the MEG response to a task with a result of an attention test. So we have some MEG results and we have attention scores for the different subjects, and the question is, are these correlated or not? Yeah, this leads me to the end of the overview of what BESA Statistics does. All tests in BESA Statistics use the cluster permutation testing approach, and let's now have a look at this in practice. So let me go to BESA Statistics. This is the starting window of BESA Statistics. On the right-hand side, we can now choose from 3 different workflow types: t-test, ANOVA, and correlation. Let's start with an ANOVA project. The next thing I now need to do is to tell the program what data type I want to work with. So I will start with a standard ERP experiment. So I'm going to choose data type ERP and subtype EEG. We will now analyze the effect of auditory tones played at different intensities to normal subjects. So I'm going to click the Start button. And now I need to select the test I'm going to use. I will use a within group test because we just changed the condition within the same subject group. And I'm also going to work with a covariate of no interest. The number of trials that were used for each individual subject may have affected the result in some way. And if that was the case, I want to factor it out. So I'm going to check that box. And I can now proceed in the workflow again using Next, or I can simply press the space bar on the keyboard at any time to advance to the next step. Yeah, now I've moved to the workflow step define experimental design. On the left side of the window, I can see the complete workflow overview, and we can see that we are in this step now, define experimental design. I had 4 different intensities. So the number of factor levels is 4, and I had 10 subjects. 10 subjects. The condition names, I call them 60 decibels to 100 decibels. These were the different intensities of tones played to the subject. So we had 60 decibels, 70, then we had 90 decibels and 100 decibels. And the covariate of no interest is the number of trials. Then go next. Now I need to load in the data. So for each condition, I need to first load a text file which contains my trial information. So first things to do, load the data for the number of trials. And I need to find that data, of course. They were on the desktop in my computer. So this is a text file with the number of trials for the 60 decibels condition. Then the next one, I can just press the space bar, is now to load the actual experimental EEG responses to this. And I can see the files of type, so I can choose between ERP files, which are saved by BESA Research, or I can also use Brain Vision Analyzer file type. So these are supported, and I can just select one of them and press Ctrl-A to mark them all, and then open them. Yeah, and then I need to repeat this procedure for the other 3 conditions. So let me go to 70 decibels, number of trials. You can see how the number of trials show up here. And then load the data for the 70 decibel case. Just press Ctrl-A, open. Now we need the 90 decibels. Open these. And finally the 100 decibels. And open these as well. Yes, and now the last step in this workflow here, in this step, is to accept the data order. So I will need to ensure that I correlate the right subjects with each other. So in this case, they should all be in the order S1 to S10. I just quickly browse through here to check if that is the case. And it is the case. If it wasn't, I could click into any of these and change the position using these arrow markers. So this this is important. To for the right covariate to be factored into the equation with the correct response, but also if I do my permutation testing, permutation shuffling, I want to make sure that I shuffle the conditions between the correct subjects. Okay, then go next. So now I can run a preliminary f-test, and I can see the map of the f values. And also in the channel display on the left, I can see now the first condition displayed for one of the channels, and in the display left box here, I can also choose to see the overplot of all conditions, so all 4 responses. And I can change the latency to go through my data and see how the map changes. So obviously quite a lot going on here. You can also change the channels to see different channels. Yeah, no, these red, mainly red boxes here, these are the masks that show me that the initial test showed up a significance. So there's plenty going on, even at around 0 stimulus time. And let's try and bring some order into this chaos by moving further in the workflow. So I have 3 settings up here on the right where I can make adjustments. And for ERP, especially important is the neighbor distance. So by default, that's set to 4 centimeters. And a good setting is one where the average number of neighbors is approximately between 4 and 6. So that will then enable the cluster to grow in space. But it also means that not all electrodes are directly neighboring each other. So let me just leave the settings as they are right now and proceed and run the statistics. And before it runs the statistics, it gives me a little summary of my settings. And it shows that the 4 centimeter setting resulted in an average of just 2.2 neighbors per channel. That is maybe a bit too little, so I'm going to cancel and go back and increase this neighbor distance to 5 centimeters. And again, this is something that really depends on your individual setup of your electrode configuration. So run statistics again. So now my 5 centimeters resulted in an average of 4.45 neighbors per channel. I think that's quite a good number, so that should allow the clusters to develop. And I'm going to run the statistics now. And that's the result. I can see that there are 2 clusters shown here by the reds and blue stars on the right. 2 clusters with one highly significant and one significant, marked by the red and blue stars. By default, I see the channel with the highest F value plotted here at the bottom. If I move through the time, I can see how channels get added or subtracted from the cluster. So we can see how the cluster evolves over time and space. And let me see where it starts. So the first activity, the first significant difference between conditions is observed at about 68 milliseconds, and then it actually lasts for a long time, all part of the same large cluster. Until then, at some later point, also the blue cluster emerges only at around 500 milliseconds. Okay, so now the question is, which of these conditions are really responsible for the significant results? In order to answer this, we need to run the post-hoc statistics. So let's go on to the next work step and run the post-hoc tests. This one runs several times now because it needs to do 6 pairwise tests. We've optimized these permutation tests using parallel processing, so it still should finish pretty quickly. This is maybe the last run. Yes, and now we see the result for the first pairwise comparison. So there's an additional box here showing us that it now compared 60 and 70 decibels. And we can see that none of the clusters actually survived this post-hoc testing with Bonferroni-Holmes correction. And the significance p-value here in the cluster was set to 1. That means that they were above significance level and were just discarded. But let's have a look at the other pairwise comparisons. So we can compare the 60 decibel to the 90 decibel condition. And here we see that the main cluster did survive. However, we also notice that now the temporal activation is much reduced. So the new cluster is within the boundaries of the large F cluster, but is a subcluster. Yeah, so you can see that it's only active between around about 150 and 200 milliseconds. Now looking at 60 versus 100 decibels, here 2 clusters survived. So and they are active also in this time range, a little bit later in fact, around the 200 plus millisecond range. And looking at the 70 versus 90, again, no of the cluster survived this. 70 versus 100, here we actually got 5 clusters. And these 5 clusters are actually all in early to mid-term processing stages, so between 110 to maximum 400, but mainly finishing around between 300 and 400 milliseconds. And finally, we have the 90 versus 100. And again, there's 2 clusters that survive that, and they are also one in the early and one in the later processing stages. So most of these clusters actually, if you look at it in more detail, will emerge as subclusters of the first large cluster that we found in the F-test analysis. And all the results can be exported for more quantitative analysis and reporting. So there's an export menu where you can either export images in high resolution or as vector graphics, or you can export the summary or the detailed results of the cluster statistics, which also show up here in the bottom information window. Good. So now let's look at some different data. So I'm going to finish this project. I can save it, and at any point in time I can load it in again if I want to. So just give it some name. And I'm going to start a new ANOVA project. I'm now interested in the auditory processing of more complex auditory stimuli. So the subject listened to in-tune chords, to out-of-tune chords, and to chords where just one of the chord components was delayed. Yeah, there's a source model for the processing, and a time-frequency decomposition was done. So that means we need to select the data type as time frequency source waveform and start the workflow for this. We're now looking at just a within group without a covariate of no interest, so just a standard ANOVA. And the experimental design is with 3 factor levels, and there was 15 subjects. And just for simplicity, I'm going to stick with the standard naming for this demonstration here. Condition 1 to 3. Go next. And now I need to load the data again. Condition 1. And please note that the data type is now different. We now have time frequency coherence files here as data type. Condition 2. And condition 3. Data order, let's have a check that we have the same order in all files. Yes. So go accept and next. And now run the preliminary F-test again. And now we see a different type of display. We see time frequency display. So one thing I need to say is that we had 6 different sources in this source model, one in the prefrontal cortex, one in each side of the auditory cortices. We had a couple of other sources as well that had some suspected activity. And each of them have 2 orientations. Since we have an MEG data set here, so we only need 2 orientations for each regional source. So these 12 sources are plotted here. We can also zoom into this display a little bit if we want to, and we can select which one's plotted at the bottom, and we can also get rid of the mask of, and then of course display either condition 1, 2, or 3. So yeah, this is the typical BESA time frequency display look here, and we can see by the mask where there's some suspected F-test significance. We can, I want to restrict the analysis to the delta to beta frequency band. So I'm just going to work between 4 and 24 Hertz. And otherwise, I'm going to leave the settings as they are and go next and then run the F statistics. We now do not need a nearest neighbor distance because the sources are by definition independent of each other and the clusters can only evolve within a source. So they have the chance to evolve in time and frequency, but not between the sources. So we get 2 clusters as a result with significance. One is in the R1 channel, which is an auditory channel, and the second one is in the R6 orientation 2, which is in the auditory, in the prefrontal cortex. Good. So there is some difference between these conditions, but which ones are now responsible for the differences? So again, this needs to be found out by using the post hoc testing. And this is it finished already. So condition 1 and condition 2, they actually keep both of these clusters. We can see that the clusters survived this test. In fact, have a high significance now. If I look at condition 1 and condition 3, there's no significance. I can see this cluster here, but it's actually only because the visibility flag here is switched on if I select it, but the cluster is not regarded as significant. And condition 2 versus 3, same thing, there's no significance here. So the ones that differentiate are the condition 1 and condition 2. Yeah, and again, I can export these results, of course, I can analyze them further. I can check on the different latencies, frequencies to find out where my where these cluster events are in time frequency range and so on. Okay, I'm going to finish this and again save that project. And then I get back to my initial mask here. And the last thing I would like to walk you through is the correlation workflow. So I can start a new correlation project. So yeah, just to make 3 is a good number. So we again work with an auditory example for the 3rd time. And here the question was whether there is a correlation between the strength of source activation in auditory processing and musical aptitude. The data that we use for the following example were kindly provided by Peter Schneider from the University of Heidelberg in Germany. Part of this data was used in a publication by Schneider et al. In Nature Neuroscience in 2005. And Peter Schneider investigated differences between musicians, professional musicians, amateur musicians, and non-musicians. And these subjects listened to instrumental sounds, so natural instrument sounds passively. For each of the subjects, a musicality index was also established using the AMMA test, the AMA test for musical aptitude. The tonal score in this experiment, in this test, was used for the experiment, and the score can lie in a range between approximately 20 points if somebody just randomly guesses during the test, and 40 points for the total musical people. Okay, so I'm going to select the data type SWF since we had a source model for these auditory stimuli and we have the source waveforms present. Now the number of subjects is 18. The covariate of interest is the AMMA tonal test. Those 2 variants, this was the tonal variant, and the data are musicians. So we're looking at the professional musicians here. So now I need to load the data for the test result. So these are the data for the test results. So you can see they range between 27, 23 is maybe the lowest here, and 39 for the most, I suppose, most musical people, or at least most person who performed best in this tonality test. And the data for the musicians are, so here, sorted by in alphabetical order. So I need to make sure my data are in alphabetical order, because so are the tonal test results in this file. So that looks okay. I can accept the data order and go to the next step. This step now shows me the two sources that were used in the head schemes, and we can run a preliminary correlation analysis where we can see on the left-hand side now the waveform of source number 1 and the mask for significance. On the right-hand side, I can show the R values and can show the mask too if I want to. Let me switch to the other source. So in the other source, similar picture. You can see that in both sources you have some significance in the baseline and even around the stimulus directly. And let's see what happens now if we perform the correlation. I'm going to be a bit stricter here with the alpha, so I'm only allowed to build up the cluster if we get below significance of 0.01. And now I'm going to run the statistics. Okay, that's a very fast test. It's already finished. I can see that I get one significant cluster where we have a significant correlation between the musical aptitude and the auditory response, and we have one trend. So the trend is one that didn't quite make it to significance, but is less than factor of 2 outside of this significance. So remember that we, because it's a two-sided test, even though p is smaller than 0.05, it's not quite enough here to get us to full significance level. And the interesting thing is that the remaining cluster, so first of all, we can see the baseline effects are no longer significant. So that has been identified as a false positive in the initial testing. And we can see that the significant correlation starts in early auditory processing, so around about 54 milliseconds already, up to around, go to the end, 86 milliseconds. So this is even before the N100 or N150 comes into play. And this is where already, this is actually the only time where there's a significant correlation between this aptitude and auditory response. And that's exactly what Peter Schneider also published in Nature Neuroscience, which was against earlier theories that the very early processing steps are the same in basically every human. And yeah, similar for the trend, that happens in the other sources, not quite significant, but also similar result. Yeah, we have data also for non-musicians, but I won't tell you the result now to keep the suspense up a bit in case you want to come to one of the BESA workshops next year. Right, yeah, so there's a lot more to BESA statistics, but we're running out of the time for this, so I just want to point you to, yeah, more information is on the wiki again, especially about FAQs, recipes, how-tos, and so on. So we're now at the end of this talk. Yeah, thank you very much for your interest, and yeah, talk to you soon, hopefully.